So I will define so-called Lipschitz, being Lipschitz, a function f, or okay, say phi, from a metric space to itself is called Lipschitz. Okay, Lipschitz. If there is some lambda positive, okay, so that d fx fy is less than lambda times dxy. So it is kind of close to being contraction, but here lambda is just any positive number, not necessarily less than 1, okay? And in our case, we will use it as follows. Okay. So back to the proof. You see, my differential equation or initial value problem were given like this. And this f was defined on some rectangle like this, right? And here is x0, y0, and this is our rectangle, and it was defined like this: x minus x0 is less than a, y minus y0 is less than b. So this side is just 2a, and this side is 2b, right? Okay, so my assumption was what? My assumption is the following: f xy and its derivative with respect to y, both of them. This is also a function of xy, of course. Both of them are continuous. So f is continuously differentiable with respect to y, are continuous on the rectangle R. R is of course this rectangle, and it's a closed and bounded subset, therefore it is compact, right? Which is a compact subset of R2. Well, both of these functions are continuous on this compact subset, therefore they have maximum values. Okay, hence both f and del f del y have maximum values on R. Okay, say we have this: f of xy is less than m. Say, okay, there are m, and let's say lambda, so that f xy is less than m, and del f del y xy is less than lambda for all xy in the rectangle R, right? Both f and del f del y are uh, bounded functions because they have a maximum value and minimum value also. So I just look at the absolute value function. These are always non-negative, but they are bounded from above. And let's say that bound for f is m, and for uh, del f del y, that bound is lambda. Okay, so you see how we make use of the concepts we have built it up so far, right? Compactness and so on. Okay, now remember in the theorem I need to define uh, this delta, right? I have to choose delta so that on that delta my solution function phi x would be defined. So I have to choose that delta. This is how I will choose it. Now I'll tell you how we pick up delta. Okay, choose delta. Uh, okay, first let me okay, now first let me say this is not lambda, but okay, L. All right. Choose fix some lambda positive, but less than 1. Okay. We fix some lambda which is between 0 and 1. Maybe, yeah, here in the definition, let me choose this file also. Okay. Now I choose some lambda between 0 and 1. Choose delta positive so that okay, wait a minute. Okay, delta lambda over m. Okay, maybe wait a minute. Lambda. No, no, no. Oh, okay, this b over m. And bir saniye. Okay, let me tell you what I'm going to do. You see, we define bir saniye. Okay, yeah, I want this and lambda less than 1 over L. No, 1 over lambda. One over L. Yeah. So we want to choose this lambda delta to be less than b over m and 1 over L. How I will do this? Okay. Yeah. Okay. Well, this tells us what? You see, uh, I had this equation, right? Y prime x is no yx is equal to y0 plus x0 to x f of uh, t yt dt, right? Okay. Uh, let X be the metric space of what? This is the uh, continuous functions on the interval x0 minus delta, x0 plus delta, okay, with the supremum metric, okay. We know that, so here is x0. I'll go up to delta units, and my functions are defined on this interval. But I take actually closed interval. Yeah, closed interval. Of course, uh, since this is a compact set, these functions are uh, all of them are bounded, and we know that this is a this is a complete metric space, right? We know that X is a complete metric space. We proved earlier that continuous functions on a closed interval AB forms a complete metric space. Okay. We will see the following. You see, okay, define uh, theta from x to x as follows. Phi of uh, phi of y. So, okay, theta of phi is equal to what? Or let's say, yeah, it is this. Okay, if Phi is a function. So continuous function on x0 minus delta, x0 plus delta. Let theta phi be the following function. This will be a function and its value is just y0 plus x0 to x f of phi f of t phi t dt. Okay. Uh, I have to make sure that this function also is defined here. Okay. How can I make sure that? Well, you see, phi. Okay. Uh, okay. Yeah. First, we claim this. This function phi uh, at any point x takes values between y0 minus m, y0 plus m. So what I mean is this. I will start with a function. I will start with a function. Okay. Like this. I will apply theta to this function. I will obtain some other function, theta phi. But I want to make sure that at least in this delta neighborhood, the graphs stays in R so that I can use this bounds like I have this L and uh, M. I can use this bounds. Okay, so if the graph of this function goes outside this rectangle, then I cannot play this game. Okay, I cannot play this game. So let's see why this is the case. You see, phi x no, theta phi x. Whenever phi is in x. Okay. All right. Why this is true? Well, theta phi x is just x0, no, y0 plus this. Sorry. So its absolute value, its absolute value, or maybe I write this way. Oh, okay, okay. Yeah. Theta phi x minus y0 in absolute value is equal to the absolute value of this integral. But you see, this integral is less than what? This function is less than m, and right, the value of this function is always less than m. Fxy is less than m, and uh, So this integral is less than m times x minus x0. But x minus x0 is what? X is here, x0, and I have this delta interval, x is somewhere here. So this is less than delta. Yes, and m minus, okay. Uh, all right. Okay, so okay, taking the wait a minute. So this will be less than m if okay, I choose this lambda delta. Okay, yeah, this is less than b. All right. Yeah, that's the so okay, yeah, we are done now, right? Lam delta times m is less than b. Okay, less than b, less than b. So this means what? Theta phi x is in the interval y0 minus b, y0 plus b. Therefore, the values of this function stays in the rectangle, right? The rectangle we had was this. So this is the y0, and you can go at most b units up and down. So I am done. Okay. What else? Uh, so this function, then theta, takes a function defined on x0 minus delta, x0 plus delta, to a function x0 minus delta, x0 plus delta. We know this. We claim that theta is a contraction mapping. Why is that? Well, you see, uh, uh, theta, uh, let's say phi 1 minus theta phi 2 x. What is this? This is just y0 plus x0 to x f of t phi 1 t dt minus this gadget. It is just another y0 minus x0 to x f of t phi 2 t dt. Well, what is this? Y0s are cancelled, of course. So we get the following. X0 to x. I have f of t phi 1 t minus f of t phi to t, and then dt here. Okay, dt here. What about this gadget? What about this gadget? Uh, for this, I can use mean value theorem. How? You see, uh, f of, okay, x y1 minus f of x y2. What is this? I can use the following fact. Here x is fixed, y is the variable, so I may think of this as a function of a single variable, which is the y coordinate, and I can use mean value theorem. What it tells me that this distance is the derivative of this function with respect to its variable, which is y in this case, evaluated at some point. X is fixed at some point, let's say some y0 or y tilde times the distance between these 2 points, y1 and y2. But we know that this here uh, gadget for our function, right, is this derivative was less than, what was it? Yeah, that derivative was less than L, and L times delta was less than 1. No, no, no. I should choose this to be lambda, this lambda. Okay. Okay. So del f del y is less than L, and uh, I had fixed some del lambda, and this lambda satisfies, or uh, delta satisfies this. I choose delta so that delta times L, this bound is less than delta, so that uh, so that so that you see this thing, this is less than lambda over what was it? Yeah, this is less than L, and this is less than lambda over delta. Okay. Is it like that? Okay, so yeah, this is less than uh, delta is less than lambda over L. All right, so this is y1 minus y2. Let me keep it like this. Now back to the integral. So this gadget is less than y1 minus y2. Y1 minus y2 is less than what? This is less than, this is in the rectangle. Therefore, this thing is less than okay, okay. So theta y1 x minus theta y2 x is less than uh, integral x0 to x, but this gadget is less than L times y1 y2 y1 x y2, not y1, of course. These are just phi1 phi2 phi1 t phi2 t, yes, dt. And okay, I can replace this by the supremum metric, right? So this is x0 to x L times the submetric between phi1 and uh, phi phi1 and phi2, because this distance, this thing is compared to this is always greater than or equal to, this is the supremum of all these, dt. But now this thing is a uh, number, so I can take it outside integral, and I get x0 to x L dt, and this thing is what? This is just the distance x minus x0 times L, but x minus x0 is less than, this is chosen to be less than delta, and L times delta is less than lambda. So this thing is less than lambda, and lambda was a fixed number, right? Lambda was a fixed number less than 1. L times delta is less than lambda, and lambda was less than 1. Okay. So what we see is then this gadget is less than this number for all x in x0 minus delta, x0 plus delta, right? For all x. So if I take supremum here, supremum of these numbers, I get what? D sub of phi 1, no, theta phi 1, theta phi 2 is less than lambda times d sub of phi 1 phi 2. Okay, and lambda is less than 1, since lambda is less than 1 and positive, uh, we see that this theta from the it's a continuous map defined on this, it is the space of continuous functions on this interval, is a contraction mapping. Okay, contraction mapping. This is a complete metric space, and I have a contraction mapping. Therefore, theta must have a fixed point. Hence, theta has a unique fixed point, say phi, okay, phi, a continuous function, uh, defined on this interval, and it's a fixed point means what? What is this? This is just a function. So, okay, implies what? Okay. The value of this function at x is equal to the value of this function at x. But what is this value? This was defined like this. Right? This was the definition of theta. Okay. Yeah, we defined it this way. So this means what? Hence phi x is the unique solution of the integral equation. Which integral equation? This one. Y x is equal to y0 plus x0 to x f of t yt dt. Since this is the unique solution of this integral equation, it's also the unique solution of the initial value problem. Thus is the unique solution of the initial value problem. Which initial value problem? This one. Y prime equals fxy, y of x0 equals x0. Defined on, of course, this function is defined where it is not defined on the whole rectangle, it is defined only on this interval. X0 minus delta, x0 plus delta. Okay. And this finishes the proof. Okay. Uh, the theorem. Existence uniqueness theorem of ordinary differential equations. Any questions so far? Sorry, I got confused in the middle, but then I think we succeeded writing the correct argument. It's kind of lengthy, but steps are simple, and we make use of almost everything we have used so far, right? We use compactness, we use completeness of function spaces, and many other things so far. So this is a really nice application of analysis to differential equations. The most important theorem of differential equations is proved this way. Okay. Next application. So second application uh, will be Bayer category theorem. Let me state the theorem, but I'll prove it next time. So theorem. Okay. Okay. So let XD be again a complete metric space. Complete metric space. And En is a sequence of closed subsets of X. Okay. If the union E of ENs, so I take unions of all of them, infinitely many of them, but countable union, right? This is not an uncountable union. I have E1, E2, E3, and so on. Countable union. If this union has non-empty interior, then uh, one of ANs must have non-empty interior. Okay, so that's the theorem. I think this is a very beautiful theorem. Why is that? You see, it tells us the following. If you have subsets, which are closed subsets, and if they have all empty interior, and if you have countably many of them, E1, E2, E3, E5, E4, E5 till infinity, then their union has also empty interiors. Okay, the union has also empty interior. In other words, you know, if you just want to have a set which has non-empty interior, and if you want to write this set as a union of some closed sets, you have to make sure that at least one of them has non-empty interior. Putting just empty things, infinitely many of them together, wouldn't give you something with non-empty interior. That union has also empty interior. Ben bunu genelde şöyle diyorum, hani içi boş nesnelerden sonsuz tanesini yan yana koyduğunuzda dolu bir şey olmaz. Onun hala içi boştur. Değil mi? Bu onu söylüyor tam olarak. Tabii sonsuz derken sayılabilir tane sonsuz. Hani uncountable değil de sayılabilir sonsuz olması lazım. Mesela bunun bir uygulaması şu. Example. Take xd to be R with absolute value metric. Okay. And consider this Q, the rational numbers, P over Q. Okay. Q is not zero. The set of rationals. This is a countable set, right? Q is countable. We may count all the rational numbers. So I can write this as the first rational number, second rational number, the third rational number, and so on, nth rational number. And you see, let En to be this singleton as a subset of R. This is a closed subset, a closed subset, closed subset with what is the interior of En? It is of course empty because a singleton has no interior, right? It doesn't contain any ball, right? Any ball. Therefore, it has empty interior. Uh, and since Q is just union of these ENs, and from 1 to infinity, we see that uh, interior of Q is empty. Of course, we knew this already, right? Q has empty interior, but you know, it's an immediate corollary of this theorem. Evet, yes. Similarly, the set of integers has empty interiors. Yeah, but of course, you know, this is a trivial example. Nevertheless, you know, it shows that this theorem is something powerful. Okay, so I'll prove this theorem next week. Okay, bana Bayer category theorem. I think I'll prove it on Tuesday. I can finish the proof on Tuesday, and on Thursday I'll talk about another application. I cannot remember the name of the theorem at the moment, and that will be the end of our you know class. Okay. Do you have any questions so far? Anything you don't understand in the Banach contraction principle or this existence uniqueness theorem? Bayer kategori teorem için mi diyorsun? Yok öyle değil. Kitapta var aslında. İstersen bir bakabilirsin. Yani onunla alakası yok. Bu şeyin contraction mapping'in bir şeyi değil. Sonucu değil. Onunla alakası yok. Hı hı. Okay. Let me stop the recording.